Okay, yeah, well, good afternoon everyone, thank you for joining us. My technical lecture title is short and snappy. It's the understanding machine hydraulic efficiency and methods of optimization. So, oh yeah, it's a dreadful picture of me, so sorry. My name is John Starkey. I'm a product director at Husco. I'm based, I'll talk a little bit about Husco in a second, but I'm based up in Runcorn, up in the sunny northwest. It's my 25th year at Husco, the end of this month. I'll have been there for 25 years. Started as a design engineer, worked through various roles in engineering, and now I'm a kind of a product director. So effectively I manage, in the UK, I manage a team of engineers and look after a lot of the engineering for out of Runcorn, and you know, we service into mainland Europe. I work with lots of OEMs. I hate to single any of them out because they're all as important as each other, but JCB and Caterpillar would be good examples of two very large OEMs, which I deal with on a almost daily basis. And then I also have kind of a global role with regards to developing and directing, you know, new products for Husco. So I appreciate we're not exactly a household name, so I won't do the hard sell, but you know, Husco. So we design and manufacture hydraulic and electromechanical components and systems. We actually, so I'm from the off-highway division, but Husco in itself is also has an automotive or on-highway division. So crudely speaking, of our kind of $550 million revenue a year, sales a year, that is about 50-50 between on-highway and off-highway. That's not necessarily on purpose, it's just how how we are, and that's how we're split. It's worth just jumping back to this. We really do like to, this is for both off-highway and on-highway, but really we like to consider ourselves as a partner supplier to our customers. Globally, so we're an American company, if you didn't know that. We have 6 manufacturing facilities. So we're based in the US, in Wisconsin, which is the state kind of north of Illinois, north of Chicago, where we have 3 manufacturing facilities. Then in Europe, in the UK, in Runcorn, we have manufacturing and engineering. And then we also have a facility in India, in Pune, where again we have engineering and manufacturing. And then also in China, in Shanghai, and again we have engineering and manufacturing there. Globally, 1,500 employees, not quite sure how up to date that is, but it's about that number. And we are heavily engineering led. You know, our owner is an engineer. His father, who was the kind of previous owner, you know, was an engineer. My boss is an engineer. Lots of engineers at Husco, great place to work if you like engineering. So, you know, our sales team is, you know, are all engineers. So we're very much engineered. So, you know, of not a huge total number, a lot of degreed engineers in there. And I touched upon it briefly, but yeah, we're still family owned. So, and it's, you know, it's a pretty, you know, the Ramirez family are still heavily involved in day-to-day running. Austin Ramirez, who's currently running it, the CEO, you know, he regularly visits all the facilities, and, you know, he knows what we do. He's really interested. He's very hands-on. And, you know, there's pros and cons of family owned, but, you know, decisions get handled fast. And, you know, he's very much in, just like his father was, you know, very much into, you know, the longevity of the business. And, you know, there's peaks and troughs in any industry, and especially the industry we all work in. And being privately owned and with a long-term view, you know, we think we can ride those good times as well as the bad times well. So, technology. So I'm just going to be concentrating on obviously the off-highway stuff. So what do Husco do? What's our technology? So in no particular order, but it kind of makes sense. Cartridges, so solenoids. So this is really, I'll be honest, it has developed from our on-highway division, where we do a lot of cartridges, and it's all to do with basically fluid control. And we lent into that as we saw the market becoming more and more electro-hydraulic based, more and more EH. Instead of relying on some of our competitors, you know, we lent into like all the knowledge we already had to start developing our own cartridges, and we have a whole family of low pressure and high pressure solenoids. What can we do with those solenoids? Well, we can use them in various different products. So we also now offer quite a range of subsystems, and bespoke is really kind of best summarises Husco. We're not big on catalogues. We really like to offer bespoke solutions. So yeah, cartridges, we can sell unique little, subsystems. That one in there, in fact, mounts directly onto a transmission for a forklift truck. And that's, all kind of bespoke for that customer. We've got some Husco solenoids in there, as well as some other, temperature sensors and so forth. I talked about EH control, so software and controls and controllers is a bigger and bigger part of machines. So anyone who works on machines, there's a lot of ECUs and a lot of electronics in those machines now, and then that's, no difference to cars and other things. So software and controls has actually been part of what Husco's done for quite a long time, and it's only kind of getting bigger and bigger in what we do. And then finally is main control valves, so really the kind of bread and butter of what Husco does. So these valves, well, you'll see in a second, but hydraulic control valves really controlling, the dig arm on an excavator, the forks on a forklift truck. So that's a very rough overview of what Husco does. Where does all the Husco products go? Well, onto a range of machines. So what I've got here, these are all products produced in our UK facility up in Runcorn. As lots of customers, lots of applications. So very briefly, backhoe loaders. So what you guys might think of as a JCB has been heart and soul of what we've done at Husco for a long time. And it's not just JCB we also supply Caterpillar, Hidgemec and a few other ones. Moving on, material handlers. So telehandlers is a huge growing market in both construction and agriculture. Speaking of agriculture, so also tractors and so forth, we do a lot of front axle suspension valves for tractors, as well as hitch control and auxiliaries and so forth. Touched upon forklift trucks as well, so Hyster-Yale manufacture a lot of forklift trucks in Northern Ireland, in Craigavon. And then there's some other bigger, so we also, out of the UK for various reasons, we also supply product out to Korea, where Volvo make some of their larger excavators, and then we also supply out to Scandinavia for some of the forestry applications, and then Cat dozers, actually they manufacture in Europe, but they also manufacture out in Brazil, and we also do supply other valves out to Brazil, and as you're all aware of, tariffs and various things like that, we could actually become more and more of an export hub. So very briefly, that's where Husco products go. That was a very, hopefully, brief and not too salesy kind of take on what and who Husco is. So into the meat of the presentation. So the landscape of a traditional machine. So this is a crude picture, but this is kind of, if you think of that JCB backhoe, and when we look at understanding efficiency and optimizing it, we really have to start with breaking down the system and understanding where the energy losses are. So very simplistic diagram. We have diesel, fuel, which goes in the front. We have, in a traditional machine as at the moment, we have an internal combustion engine. And then really, this is where we get into like the losses of everything. And then we've got, the losses of the diesel engine. And then, in the hydraulics world, we go straight into the pump. That could be a variable pump or a fixed displacement pump. And then there's going to be losses associated with the pump and also, the energy management of that pump. Then we come into the main control valve bit. So for those who don't know, this is a spool. So it's a very crude approximation of the hydraulic valve. And then we've got the hoses and the fittings and any other auxiliary valves. And then eventually you get out to your cylinder, and then the drag and the friction and the any internal leakages in your cylinder, and then eventually you get out to productive work. So on that digger, you're trying to dig out that hole. So diesel in, basically losing losses through to friction, heat, noise, all those things, and eventually you actually get some productive work out. So understanding those energy losses in the machine is going to help me design a better valve to optimize them. So let's put some numbers to things. So please don't can all pick and choose these numbers, but when we talk about diesel efficiency and diesel engines, these aren't, you know, car engines. You know, these are, you know, these diesel engines have to work in altitude, have to work in pretty tough environments. They also have to be, you know, priced correctly, you know, for the market. So, you know, some of these efficiency rates, you know, are going to be a lot lower than, you know, your fancy new diesel car and stuff. And then we really go through every part of the system looking at what those losses are, because, you know, the big number at the bottom, which I suppose I should have started with, is that the actual overall conversion efficiency from, you know, diesel in the front bit to that productive work, the bit we're interested in, is you know, approximately, roughly, you know, about 8%. It's not a great number. So just to quote, you know, so for your 10.7 kilowatt hours of energy per litre of diesel, this gives you an idea. You know, it's not as, you're not really getting as much out of it. You know, that's why your fuel tanks are so big on these things. So, like I said, you know, you could, I'm not going to do it, but you could go to town and make your, you know, your diesel engine more efficient and those other things. But we're going to, you know. So, the landscape of a present day machine. So lots of OEMs, lots of customers have started to look at how can they make, you know, their machines more efficient and more, you know, optimized. And really the kind of present day, or the what I would call like the first generation of doing this, is really looking at that energy source. So, you know, JCB have got electric machines now, you know, which have got batteries in, and they really haven't changed anything. They've just kind of put batteries on their machines. Or, you know, for decarbonisation and you know, you could look at using, you know, like biodiesel fuels, you know, and those things, you know, to reduce the carbon emissions from how you actually create that diesel fuel. Or, you know, if you're looking for zero emissions, you know, hydrogen, and, you know, certain OEMs and certain, you know, customers are really looking at going, you know, deep into hydrogen to, you know, reduce those, you know, carbon emissions from the beginning, and then, you know, like I said, battery power and so forth. So there's practicalities of all of this. Big mining machines, it's just not going to be practical. It's practical to go electric. In fact, some of the really big mining machines, you know, are you know, already electrically driven now. But, you know, those big 20, 50 ton excavators out into a mine, it's just not going to be very practical to put batteries on them. So really, for a lot of these present day machines, it's more the kind of compact machines where it's more of a sweet spot. So by a compact machine, it's the kind of machines you would drive by on the road. So mini excavators, you know, backhoe loaders, you know, telehandlers, those kind of machines. So they're a reasonable kind of sweet spot for where you can change this energy source and actually get, you know, still have some degree of you know, you can still use the machine in a practical way for, you know, a long working day. However, so that's the energy source bit, and that's what people are doing now. So where do kind of the hydraulics and where does Husco come into this? So we can affect pretty much this bit. So leaving the energy source. So we're fairly agnostic to what that energy source is. So, you know, if you do want to go to, you know, an electric system to drive your pump, that's fine, or an IC system, because of all the stuff we're going to affect, it doesn't really matter what energy source you've got. So very crudely, what can we affect? So with regards to the pump, Husco don't make pumps, don't worry. But you know, we do offer software and so forth to look at, you know, improving, you know, power control, and we can, you know, by making the main control valves and understanding what's going on, then we can offer much, we can really tune the power control on the pump to work, you know, in harmony with the main valve. And then also, obviously, the kind of bread and butter of Husco is the main actual valve itself. And obviously, we can look at how can you make that more efficient. You know, is it purely by making it bigger? Is it, I don't know, distributing it out to the cylinders? Is it, you know, looking at, you know, on purpose, you know, regenerative of flow on the cylinder? So lots we can do with the main valve, and I'm going to go on to some more of that. And we kind of go all the way out to the cylinder, because no, we don't make cylinders, but we can also affect, obviously, like I said before, you know, those losses, you know, instead of the return flow going all the way back to the valve, we could do a cylinder mounted device, which we can then, you know, lower those losses by, you know, regenerating the flow more locally to the cylinder, sorry. So all of that hopefully gets us increased productive work, which is the main goal of everything. So we reckon we've got a chance of about 30 to 50% of the total energy is the bit we can actually work with. I've made a point of saying, any questions at this point, because I do talk quite fast, and I do cover a lot of stuff. So that's kind of the background. So, okay. So to be able to improve all of this, you've got to understand the machine and the complete machine. You've got to understand all the way from the operator's commands to all the way through to literally the earth moved, to the soil moved. And, to put that into kind of, why is that? Because we've got to understand all that litre of energy, all that kilowatts of energy, all the way down to how much actual kilograms of earth moved. So what have we been doing over the last 20 years? We've benchmarked a lot of machines. I'm going to go over what we do to benchmark a machine in a second, but this gives you an idea. And what's fascinating is that, big excavators, backhoes, mini excavators, wheel loaders. It's funny because as you test all these machines and learn about them and learn all this, there's a lot of similarities. So it's great, really. So the surprises get smaller and smaller as you do this stuff. And then, even on a dozer, it's not in reality much different to, a wheel loader and stuff. So over, 100 machines sounds a lot, but this is across all our facilities. So it's not just in the UK, it's not just in the States. We've done this everywhere. And we've just kind of built a bigger and bigger picture. And it's great because we do this in conjunction with OEMs. So either they pay us to do it or they give us a machine and, we're developing something new. So the whole time Husco's learning more and more, which is great for us. And, we always learn something new. But lots of machines. This has taken a very long time and it's a pretty costly process. What do we do with those machines? So I was excited by this slide. So machine testing. So whether you think or not, there's a lot goes into instrumentating a machine to fully understand what's going on and where those efficiencies are. So pressure transducers, you're going to want to know what the pressure is at the pump. Then I want to know what the pressure is at the valve. So there's some pressure transducers. Then I want to know what all my work port pressures are and what my tank pressure is. But then I also want to know what the pressure is at the cylinder, because I want to understand what my hose losses are. And then on the return flow, return from that cylinder, I need to understand those pressures from there to there, then from there to there. And I want to know my tank pressure. I want to know my tank pressure at the valve. I want to know my tank pressure upstream of that return line check. Then I want to know if I've got a pressurized tank, what that pressure is. And then I've got to do that on every cylinder. And then I'm going to want to know if there's any other, what's my pilot supply pressure is, what my accumulator pressure is. I might want to know what my sump pressure is. I want to know what my suction line pressure is. So that's just pressure transducers. Then we're also going to know, we need to understand what the cylinders are doing. So we use displacement sensors, string pots, which we mount straight onto the cylinders. So that's going to tell us what the cylinders are doing. We're going to want to know what the pumps are doing. So we're going to want flow meters on the pumps. We may also want flow meter on the return line just to make sure we're not missing a trick and missing any flow. We're then going to want to know what all the operator's commands are. So if it's an EH machine, we can probably put current sensors straight onto the current commands. But if it's a pilot operated machine, we can probably just put, again, additional pressure sensors. But if it's a mechanical machine, it's a bit of a pain and we have to go ahead and put little LVDTs on the spools to collect those operator commands. Vast all machines now obviously run with CAN networks, and we can pick off loads of really useful data off those CAN networks. So we can pick operator commands, we can pick angle joysticks, we can pick engine RPM. Often you can get kind of pump flow off them. You can get lots of good stuff. So typically we end up with about 260 raw signals off one machine. And unfortunately, a mini excavator probably is just as busy as a big excavator, so it doesn't actually particularly scale. Of those 260 raw signals, we can then analyze them in different ways, so we end up with over 1,100 different analyzed signals generated. Because what we can do is for instance, off the string pots, off the cylinders, we can measure displacement, but we can just calculate flow theoretically from them straight away. So we might as well throw that as an additional signal. So we'd have to do additional post pressure. So just to put some very crude numbers on it, we end up with about, for every kind of standardized dig process, we end up with about 1 gig of data. So, which isn't actually huge because it's just raw data. So we've instrumentated our machine. Now we've got to do some baseline testing, and this is also really tricky and hard because don't tell an operator to go and dig some holes because he'll do exactly that. And then you get him to do it the next day and he does it completely differently. So trying to come up with standardized tests is really hard. There's no official ISO standards. They're always trying to come up with, ISO productive and efficiency type style testing, but it's really hard. So you work with the customer, work with the OEM on try to standardize some testing. Excavators are a good example. So maybe a lorry loading is a pretty classic one. So you can do a 180, park your machine, park your lorry behind you, and then do a 180 slew into it. Or maybe on a backhoe or something, you might want to do like a long trench dig. So maybe a 4-foot deep trench, and then maybe I'm mixing my units, good 10 meters long or so forth, and then you can use very clever 3D cameras to work out how much you moved. Obviously with your lorry load, it's great because you can just use the weigh station on the lorry itself to weigh how much you've moved. Or you can just go in and measure every couple of feet and check that you've got a level thing. But doing a standardized test isn't easy. So lots of data from our instrumentation, try to do a standardized test. You end up with, which is the modern day problem, which is big data. You end up with a lot of data. So what we've tried to do and come up with is basically standardized plots to come up with some a means of some comparison, so some data which we can compare meaningfully to make, so if we do make a change to the hydraulic system in some way, then we can repeat the testing and compare things and look and see if we have actually made an improvement to the efficiency, which was the goal of the whole exercise. So, all of these aspects are really important, but ultimately getting good data and actually using it and being able to analyze it is probably the most important. So, one thing I did forget is the other thing. Obviously, we'll talk about efficiency. It's also measuring fuel. So again, sometimes you can do that off the CAN signal. You can just measure fuel. You can put a fuel meter in it. We've even in the old days, we used to literally have a separate diesel can, weigh it before the test, do the test and weigh it afterwards, and just work out the diesel usage that way. So this is something which Husco's come up with entirely. So this is the machine analysis of basically what we call a dig cycle. So it's the dig, dump and the return on a large excavator in this case. And then we've looked at 3 different cycles. So in this case, this is the dig cycle, the 3 different dig cycles. And then what's interesting here, why this is highlighted, is that these are the operator commands. And for some reason, the operator in this dig cycle accidentally used a little bit of slew. And then so he's got a tiny command of slew, and then that's ended up blipping this pressure here. So we've ended up with kind of erroneous data because the operator wasn't, he didn't know he was doing that. He did it by accident. But he's just done something which just added an inefficiency. So as always, the best way of improving efficiency on the machine is actually get good operators. But from a kind of standardized test data point of view, that's not a great plot. We want to look at more standard plots where you can see the commands are very similar, and then you end up with very similar pressures and flows. So we take all that, and then like I said, we put it into this kind of box plot where, as I said, we've literally split the cycle into the dig, the dump and the return. And then within that dig cycle, we've split it up between the different services, between the boom, the arm, the bucket and the swing, to see exactly how much energy we're losing. How much energy is being usefully used, and then how much of that energy is hydraulic losses. So the dirty yellow, which isn't that particularly dirty on this screen, dirty on my screen, but is kind of the opportunities where the hydraulic losses could be reduced. And then further to that, you've also got where, quite easily on a big excavator, where you've got boom down, where it's effectively a gravity service, where there's potential to actually store energy. So there's potential energy. You don't have to put any energy into the system. You could actually reuse some of that potential energy. So obviously these are theoretical maximum values, but that's how much energy you could actually recover and store or use elsewhere. Okay? So, complex nonlinear systems, so lots of machines take lots of data, use that, come up with some kind of automated process where you get good, consistent dig data, you analyze it in a consistent way where you can easily compare cycles, so you can see if you're making improvements or not making improvements. Use all that information in your next improved product design. So that's what Husco have done as we've launched, well, I'll come on to that, but as we've launched our new kind of range of valves, we've used all this data, all this machine data, all this analysis to come up with an improved product design. We're not just coming from nowhere. We're not just, hearing following what the competitors are doing or looking elsewhere. We're trying to be, as always, data focused, use the data to come up with an improved product design. Any questions about machine testing and our approach to analysis? Okay. Everyone's had lunch. Everyone's relaxed. So the challenge was really to come up with a common machine platform which we could use on various applications. Husco, we like to go on various different applications, but have one machine platform. We wanted to lean into all the other systems which are already out there, so the best-in-class configurations across the market. There's lots of different valve solutions already out there, and they all have their pros and cons, and we didn't want to ignore them. In fact, what we wanted to do is take the best bits from all of those, which is what we did with the Husco MX range. So, common platform, taking the best bits from everything. At its heart, the MX platform is a flow sharing post-pressure compensated valve, PCLS valve, LUDV if you're German. So post-pressure compensated valve. However, we did want to make sure we took the best bits from all the others. So we also wanted it to be simple, future-proof solution where we could, as well as doing PCLS in it, we could also do any circuit with using the same family. Some of what we're hearing from the market, what we saw with competitors, and what we also know operators want is kind of multifunction, the ability to prioritize certain services, smooth operation is key as well for operator comfort. Efficient solutions, that's where we've just been talking about. So we wanted to make sure that we future-proofed ourselves for not only improving efficiency now, but improving efficiency later as circuits developed. Auxiliary flexibility, so for those who kind of know their machines, more and more machines are used with more and more different attachments and auxiliaries. They're real kind of workhorses. Backhoe or an excavator is a great example of, you can fit all sorts of different attachments to them, and you can therefore use that one machine in lots of different ways as a bit of a Swiss Army knife. This final line, which I know doesn't sound particularly technical, but there's no point of coming up with something brilliant and new which you couldn't manufacture anywhere. Our customers are global. They demand us to manufacture across the world as the world changes. So we had to make sure that it aligned with our supply chain, our global kind of manufacturing strategy as well. So the MX valve range, what can it do? Well, it's exactly that. We can right size it for the application. So the beauty of right sizing it is you end up with a smaller envelope valve. You can also make it more efficient. So again, you're optimizing it. You've got the right size sections to handle the return flow, so you're not adding any additional losses. But then equally, you don't want an oversized valve because that's just big, heavy, and expensive. So you can mix and match, make it the right size. Actuation techniques, I've talked a lot about EH, but there's still a market for pilot operated machines out there. There's still a market for manually operated machines out there. And then, like I said, at its heart, MX is a PCLS pressure compensated load sense valve, but it can also be configured to be open center, and sometimes an open center valve is what you want, and there's also efficiency benefits of open center. But you could also configure it to be used as a pure positive control system, where you've got direct control of the pump with regards to flow control, so you don't need the load sensing aspect of the valve. You could also configure it, and I'll go on this on the last slide in a second, but you can also configure this MX valve to actually use multiple pumps. So older, more legacy type valve products, especially used on excavators, use 3 pumps, and they were actually really efficient solutions, which the market's not everywhere has moved away, but has moved away from. But when you think of efficiency, splitting up the pressures and the flows per the service is actually the optimal way of improving your efficiency. So MX can be actually configured to use multiple pumps. So that's how we came up with, that's what we wanted to achieve with the Husco MX range. The final slide, no doubt you'll be pleased to hear, is MX in action, so to speak. So this is an example, development example of an MX valve. So in this case, I've picked on a backhoe valve, which is kind of the very dear to Husco, especially in the UK. So this open center backhoe valve, we've been in the market with that for 30 plus years. In fact, we made over the foundry who used to pour this for us. They presented us a number of years ago, but with our 500,000th casting, believe it or not. That's how many. So anyway, so traditional backhoe system would be mechanically or maybe even pilot control, just using good old fixed displacement pump straight into an open center valve with just a pretty basic hydromechanical pump and power control. And for many years that worked fine, but it's not particularly optimized, it's not massively efficient, and also you're looking at kind of skilled operators to use them. And the world's moving on and there's less of those skilled operators. So phase 1 with MX, in this particular case study, we jumped to EH and going to that electro-hydraulic control. For the OEM is great, it means it simplifies their cab. It allows them to do some of the safety features which you're going to need on a machine are a lot easier to achieve when you've got an EH valve, because you can cut the power, and then as a guy's getting into his machine and he grabs a joystick, nothing's going to start moving, which is harder to do in a mechanical machine. So there's benefits for the comfort of the operator, the safety of the operator, and as well as obviously the control as well. Going to a variable displacement pump, so instead of churning out fixed amount of oil regardless of what you're going to do with it, now we're only going to ask the pump to give out exactly the amount of oil which the operator is demanding. So that's already going to be an efficiency saving, and then we're going to use EH power control to match the hydraulic power demand with the engine. So now we can run the engine at a sweeter, more efficient engine RPMs and engine spot to be most efficient. We can right size the pump to work at that, but typically lower RPM, and then with clever EH power control, the operator won't see any loss of performance, and he hasn't got a load of black smoke coming out of his exhaust. And then also it's worth talking about that jump to EH makes you automation ready. So we're not talking about diggers going out and digging holes on their own, but there might be little kind of driver's assists. So the guy thinks he wants to do a nice flat grade, but he's not the most skilled operator. Without adding too many sensors, once you've got an EH valve, you can just start helping him achieve that flat grade. Or from a safety point of view, now you can do what they call like e-fencing and stuff. So I don't want to dig any deeper than 10 feet because I know 12 feet down I've got some electrical cables or whatever. So making that leap to EH kind of gets you ready for that next step, which we might not be ready for, but it allows you to make little baby steps. And then phase 2 with the MX hardware, and then this is where you want to make that next step into kind of real efficiency savings. I talked about it previously, this kind of multi-pump positive control system. So like I said, if you really want to lean into efficient hydraulics, It's instead of having one pump running at whatever the highest pressure is, why not have multiple pumps running at just the pressure required to get the job done? So that's where you can really get into big savings. So I'm always wary of offering up efficiency saving numbers, and that's because it all depends on your baseline. You know, if your baseline isn't very good, it's easy to say we're going to be 20%, 25% efficient. Obviously, if your baseline is pretty good. So to put some numbers on it, making this leap, and depending on the baseline, you are probably looking at about a 15 to 20% improvement, and that's real. However, when you start digging into this and getting, you know, harping back to all the previous slides where you look into, you know, the potential savings you can make hydraulically, that 40 to 50% number, that is some of the potential savings you can get here. You can be up to 50% more efficient. It's all a cost, obviously, versus, you know, efficiency kind of game to play, but they are the, you know, potentially the numbers you're looking at, which would be a huge step forward in the world of hydraulics. And not going to happen overnight, but, you know, I think, you know, we are slowly making that change, and just with this, you know, big drive to EH, I think it's going to make the next leap for those efficiency savings, you know, easier to achieve. Okay, that was it.